Hi, I'm Samad Shah and I belong to Team 12. We'll be doing a literature review on the problem of steering angle prediction in self-driving car. So the problem of steering angle prediction is one of the many problems that compose the major area of self-driving cars. The other problems include object detection, estimating the orientation or distance of other cars, activity recognition, and many others. As far as steering decisions are concerned, there are various approaches involved. One of the approaches is dividing this problem into sub-problems and then solving each of the sub-problems and then composing that entire solution to decide the steering angle. The other approach, which we have dived deeper into, is the end-to-end approach, which is also called behavior reflex approach, where we just give the input image data and the system outputs a steering angle. Uh, One of the first architectures that we explore is PilotNet, which was developed by NVIDIA as a part of autonomous driving solutions. PilotNet takes an input data of road images that are taken from the front-facing camera, and it outputs the reciprocal of turning radius. It uses convolution neural networks, and the work was inspired from the DARPA autonomous vehicle, that is STAVE, which was a competition held 10 years ago. Uh, and it was also inspired from Autonomous Land Vehicle in Neural Network, which was a work in 1989. The following figures show the system architecture of PilotNet. In this, we have the recorded steering wheel angle, which is shifted and rotated, and it is given to the network. We also have the images taken from the left, center, and right camera, again shifted and rotated, and given to the CNN. The predictions from CNN are compared with the actual steering wheel angle from the driver, and then the error is used to adjust the weights of the CNN using backpropagation algorithm. So this is the training system. In the test system, the center camera images are given to the CNN, and using the drive-by-wire interface, the car is steered accordingly. So the workflow is as follows. There is a data collection method in which timestamped video images are taken. Also, the steering command from the human driver is taken, and the data distribution is vast. They take data from highway and two-lane roads. The highway data is taken from Illinois, Michigan, Pennsylvania, New York, and road data from central New Jersey mostly. There are various road types as well as weather conditions considered here. The videos are then sampled at 10 frames per second. A sampling rate faster than that will result in two similar data, which will not help much in the training process. The sampled images are also augmented, shifted, and rotated so that the network is trained to correct from a wrong orientation. So this figure shows a network architecture of the convolution neural networks. It basically contains an input normalization layer followed by five convolution layers, and then the final convolution layer's output is flattened, and it is fed to a fully connected layer, and then there are a series of three fully connected layers which finally output the uh, inverse of steering angle. The testing of PilotNet is done in two stages. First stage is using simulation, where the CNN that was just developed is used to simulate the position of the car. So there is a series of pre-recorded video which is shifted and rotated and then fed to the CNN, and the output of CNN is used to update the position of simulated car. uh, and the performance metric used here is the percentage autonomy, which is the percentage amount of time that autonomous steering is done. The formula for autonomy is shown here, and then after a good percentage of autonomy is achieved in simulation tests, they go to on-road testing, where 98% of autonomy was achieved. Moreover, the car drove for 10 miles continuously without any human intervention on Garden State Parkway. There is another research paper which discusses the comparison of PilotNet and its learning with human perception. The results of this research paper shows that similar to what a human driver perceives, like the edges of the road, the lane markings, even without clear lane markings, how to keep the car in the same lane. These same objects are also learned by PilotNet and considered important. In order to visualize what PilotNet learns and considers as important, there is a visualization method which uses averaging and deconvolution to basically it basically averages the stacks of convolution layer and then uses deconvolution back to trace to the original image, and then it masks the deconvoluted mask on the original image to understand which parts are considered important by the network. This These are called the salient objects, and they are highlighted in green color. Uh, as you can see, even the edges of the lane, which are highlighted in green, are understood by the neural network as important in keeping the steering angle. Further, to validate this method, these highlighted parts of the image are shifted, and the effect on steering decisions is seen. If you observe the graph on the right hand side of the presentation, you'll see that the red color corresponds to the background part of the image, which is not considered important by the network, whereas the yellow portion is the whole image, and the blue portion is the part of the image which are salient objects considered important by the network. And as and when you keep shifting this salient objects, the steering decision vastly changes, and it is more similar to the effect that is produced when the entire image is shifted. Okay, so the next part of this presentation will be taken over by my teammates. Thank you.
Hello, my name is Minal, and I'll be discussing another topic for the self-driving car for the steering prediction problem, that is the deep steering. This is also an end-to-end driving module, which is based on the behavioral approach. It uses the Udacity challenge dataset, and also it was inspired from the previous models like the Alvin, the DARPA Dave, the AlexNet, the NVIDIA's model PilotNet, and VGG16. So here an LSTM unit is inserted as the penultimate layer, which summarizes all previous states. Also, one more thing here is the recorded wheel angles from human drivers are treated as the ground truth. So what are the main features in deep steering module? This module uses real human data, which are time synchronized with also other vehicle sensor data. This module uses a combination of spatial and temporal convolution to get the regular neural networks, and which is used at different layers. This is especially used when you need the vehicle's historical state as well as the current state. Also, it uses the visual backpropagation scheme for discovering image regions that are crucial in the final steering prediction. So this is basically the architecture for the deep steering module. The input video frames are first fed into a feature extracting subnetwork, which generate a fixed length representation feature. The extracted features are then further forwarded to a steering predicting subnetwork. Also, the black box on the arrow means a one-step information delay in the recurrent unit. The steering prediction subnetworks reads the predictions in previous state and the feedback, which are fed back from backpropagation. Here, the network actually consists of 9 layers, including a normalization layer, 5 convolution layers, and 3 fully connected layers. So we'll be discussing all the sections in the architecture step by step. So this is the first feature extracting subnetwork. So conceptually, the whole network is divided into subnetworks, and the input video frames are first fed into these feature extracting subnetworks, which generates a fixed length feature representation, which has the visual surroundings as well as the internal state of the vehicle. Now, to encode this temporal information, convolutions are performed, and with a target dimension of a feature extracting subnetwork of 128, the responses of the spatial temporal convolutions are then fed into a fully connected layer, which converts anything into a 128D vectors. Now, finally, the final feature is obtained by adding all these 128D vectors at all scales. The extracted features are further forwarded to a steering predicting subnetwork. Here, an LSTM convolution unit is inserted in the penultimate layer. This LSTM actually summarizes all the previous states. The recurrent neural networks is used in such problems for sequential learning, and for each wheel, it is used to determine both the current state and the previous state of the model. The LSTM layer is generally inserted right before the final loss, but here it is also introduced in the recurrent layers in early feature extracting stage 2. So in total, there are like 3 recurrence during the network forwarding. The first is the LSTM unit with one-step recurrence. The model concatenate the previous steering action and vehicle status with this 128D vector. Also, there is another one-step recurrence between the final output and the concatenate layer right before it. The figure shows the use of temporal unrolling for 3 consecutive time steps. Apart from that, the deep steering module uses the visual backpropagation or the VBP framework, which was proposed by NVIDIA. So the computation of the VBP actually consists of 5 states. The first is for each convolution layer, average over all channels and obtain a mean map. After that, upsampling each mean map via deconvolution is done so that its new spatial resolution is the same to the low layer. Now, perform a point-wise multiplication between the upsampled mean map and the mean map at the current layer, so thus obtaining a mask map. Now, the mask map and mean map are added to obtain a residual map. This is the final output, and thus it is iterated for above all steps backwards until the first layer. So something more about the data set which deep steering uses. It actually uses the video frames provided by Udacity that are captured at a rate of 20 FPS. The training data is collected from 2-lane roads and residential roads with parked cars, tunnels, and unpaved roads and conditions similar to that. This data is mostly collected from the roads types and conditions at California, and each video frame has a corresponding geolocation along with a timestamp and vehicle states as well. The learned steering model here is desired to tackle road traffic, lighting change, and traffic signal lights. Data collecting cars have 3 camera mounts at left, middle, right around the rear mirror, and only the middle cam video stream is given to the testing sequence. Now, the performance analysis of this model says that the use of spatial temporal convolution model actually ensures that a smooth prediction for curves are there. Also, data augmentation via mirroring, which is actually used for doubling the training set and is validated to improve the learning module by decreasing the root mean square error. Also, the key framework reductions like methods like the top region cropping or the spatial subsampling or temporal subsampling and silent feature keywords are also used, where the spatial subsampling was found very beneficial. These are some of the testing performances which gave very close evaluation to the actual angle predicted. And that's